near Leiden. At some point, I went to the university in Delft, and that's where I started to look for a job, and that's where I came in here at Weave. And at that point, it was the first time I came in contact with Go. And it was in the solicitation, there was like an assignment back then to build an API for creating a task, listing the tasks, updating them, whatever. And it was so easy, I immediately began to fall in love with Go. And around 4 years later, I'm here advocating Go to you guys. So I think that's proof of how much I love it right now. And this presentation is about going into the concurrency, the parallelism, which is built into Go, and why it's so easy doing it with Go in comparison to other languages, and I will show you some examples along the way. So let's dive into it. Oh, I need to use this one. So I start off with a little bit about threads, not too much, but I will compare it to Goroutines in general, and then I will give some examples, show you how parallelism works, and then we continue to concurrency, and I'll give you some examples where we use them right now. Oh yes, it works. So, how the original threads work, they are managed by the operating system itself, so by the kernel. And when we program some code and we want to run it, a thread is started by the operating system, and it executes your flow of code. And when it starts up a thread, it needs to allocate memory, like 1-2 megabytes of memory, and that's done already pre-scheduled by when you compile it. That stack cannot grow. It is, I think it needs 50 or more registers to allocate, and every time it switches and every time it needs to destroy these threads, it needs to free up that 2 megabytes, destroy those 50 or more registers, and that takes a lot of latency in switching to those threads. Also, there's no real, you can communicate between those threads, but that's pretty difficult, and it takes up a lot of latency. So what does Go do? It came up with Goroutines, and that is like the concurrency, the parallelism of Go, just made into the design when building Go. So the creators really thought about this one, how can we improve the multi-threading, and how can we make it easy for the developer. So they come up with Goroutines, and it's managed not by the operating system, but it's managed by the Go runtime. And it only uses 2 to 8 kilobytes, so depending on what version of Go you're using. And that's a lot less than the 2 megabytes we just saw for the threads. The stack size can grow. And why is it so small? It has some parts of the Goroutines are shared in between, and that we can come up, we'll talk about that later. And that's also why there's communication between these threads or Goroutines, and that makes it really cool to use. It's also cheap to clean up, and it's also cheap to switch, because where threads need like 50 registers to change, we only need 3 registers for Goroutines to change. So that's a pretty big difference in allocating size of memory and allocating registers and how to switch them. So, how do we use them? It's pretty much putting the word Go in front of a function means it starts up a new Go routine. And that is like simultaneously, we'll start up print A, print B, and print C at this point. And the first thing that is printed is started. So what do you guys think will be printed right now? Can anyone maybe in the front row answer? Started? Only started? Correct. Because what is the main thing of Goroutines? It is started, but if the main routine, the main thread is already exited, those will not continue. So maybe A is printed here. It depends on how fast your computer is right now, but probably not until C. B and C will not be printed, maybe A will be printed. So what can we do right here? If we put a little sleep at the point at the end, then we know everything will be printed. we do not know what order, because it is simultaneously, so probably A will be printed, maybe C, and then B, but those can change. But they start up pretty quickly, so we don't need a really long sleep, but this is already working simultaneously, so in parallel. So, what you can't do with threads, with operating system threads, is start up a million of them. Here, we could do this. It's not really a good thing to do, but you could start a million threads or Goroutines, and then we will see 1.53 gigabytes. That's somewhere in between that it was running. And you can see it uses multiple threads. So the Goroutines are not separate threads by default, but it can be, Goroutines can be multiplexed among multiple threads. So it's not multi-threading per se, but it can be multiplexed among them. So where is this being used? I think almost any API built in Go, so maybe some of you know Gorilla Mux, maybe you know some other framework, but almost any framework. Oh, maybe someone needs to use the standard remote. It will turn off in 5 minutes. But it basically means almost any framework that is building APIs, where you can build APIs in Golang, will use every request that comes in and starts up a new Goroutine. And that's why they can do many, or can handle many requests simultaneously. And this means in this graph I found on Google when I searched it, it was one of the first graphs that come up, and we can see that Go really performs well. And the funny thing is that Node.js comes in second here, but the next slide. Whoop. Maybe I need to use this. Or not. I think I broke it. Sorry? Okay. So it works again. No problem. So it's really funny because the founder of Node.js actually said, I changed my mind. I think Go just was built from the ground better than I built Node.js for certain things. So he actually said, if you're building a server, I can't imagine you do anything else than Go. So that's really funny for something that also performed well, Node.js. So we just saw some examples of parallelism. So doing things that are not necessarily dependent of each other, just doing them next to each other. But the fun thing begins when you want to do something concurrent. So it means you want to do things, do a lot of things at once, but sometimes they depend on each other. So the difference, I think, here is you can see the green line and the red lines. That just, okay, they are not dependent, they're just running next to each other. And the other thing is, I have some processes, but they need to be in order. And that's where we have an example. Let's say we have some really complicated products, and price calculation is very hard. But if you order something with multiple products, we want to see, okay, what is the price of the entire order? So then a little bit, so what we can use, for example, is a weight group. And this just means that we start up a weight group, and if we have an order with some products in it, we just add the length of those ordered products to the weight group. And when we range through those orders, we can separate, we can just start up Goroutines for each product. So that means every product is calculated simultaneously, but we know that if you do that, you don't know the total if not every product is calculated. So we can just call weight group.wait, and this means we wait until the weight group is decremented to 0. So we added the length of products, and every time we run calculate price, we go here, and defer just means at the end of the function we just process wg when done. That is the weight group. So every time we run a weight group and done, it means decrement by 1. So we do some hard task, and that means that if every Goroutine finished, then the weight group should be at 0, And that means that the main routine waits until it was 0, and then we can go again through those products and just add the price, and we know the total. So actually, for every product, a new Go routine was started, but we wait until everyone was done, and then we know the total of the prices. So that is an example of wait groups in Go. But another one is channels. And this means we have separate Go routines, so the pink one and the blue one, and they can communicate to each other through a channel. And I will explain it in the next slide. But there are a few types of channels, and we also want to show them in the two at the bottom. It means you can do a channel that is just like one data gatherer, and if you put something in, someone else can get it out, and then it's done. But you can also use buffer channels, and that just means we have a size of a channel, and we wait if it is full, and otherwise we can add it. And at the other end, we can wait until something gets in, and then we can handle it when it comes in. Is where we use a finder for ore, so maybe gold or something. We can give it to a miner that will mine it from the rocks, and then we can give it to a smelter, and then we get something like a gold bar or something. So we start up with creating a channel. So we have an ore channel. It contains strings. We have a mined ore channel. It also contains strings. And then we begin with the finder. And we start up a Go routine, and we put in a slice of strings, so rock, ore. And every time we find something with ore, then we put it into the ore channel. So that basically means we have a Go routine running, and we put something in the channel if we find something with a certain condition. Then the next Go routine, separate from this one, can just wait until something comes in the ore channel. And if something gets in, then we get found ore. And then we use something, maybe a function mine ore, and we actually see what we get is gold. And then we can actually put that in the mined ore channel. So the next Go routine, also separate from this one, that waits on the mined ore channel, we'll get the mined ore, and that seems to be, we know that this is gold, so we smelt it, and we get a gold bar. And now we have money. So this really means that we have like 3 different Go routines that are separate from each other, and not really, they are dependent on each other, but not really. They just communicate through these channels, and if something puts in a channel, then we can process it. So there are 3 different processes, and they just wait until they retrieve something from the channel, and they can process this thing. And it's really fun because this can be used in many cases in production. And it's really fun to speed up some processes that normally are sequentially from each other. And now we can just say, maybe for a channel, let's say we start up 2 Go routines that are both watching the mined ore channel, then we can process 2 of these things from the channel. So let's say we have the mined ore channel, then if we start up 2 Go routines, only one will get the first item, only the second one will get the second item. So it's not like they will both get the one item. So it's really fun how this is already managed in Go runtime. So it's really made easy to distribute tasks by using a channel. So in practice, what we are already using is APIs. So what we already showed, almost every API created in Go will use Go routines to start out to handle requests. What we can do is handle cron jobs. That means maybe we list something from the database, we get some entity, and if we get some entity, we can you can imagine maybe we retrieve 100 of them, and we can just say for every of them we start off a Go routine and we process them all at the same time. Another example of this is that we use the monthly pricing is a bit like the wait group example I gave, is if we calculate prices for every month for the Energy Zero project we already mentioned, which Peter Jan mentioned, is that we can calculate the prices for every month individually and then do that at the same time, and then we get a real quick calculation of the entire year. And another one for the pipeline is when we convert readings that we retrieve from houses to whatever usage they are really using. So the difference between those readings, and then calculate cost from them. And that's really the pipeline you just saw, is when we retrieve readings, we put them in the channel, then they calculate the usage, and those are put in the channel, and those are picked up, and the cost is calculated from them. So it's really easy and fun to use this in production. Thank you.